Welcome. My name is Bob D. Hilster, and I am a Christian who happens to like science. This video is a video that asks the question, is G a universal constant? G is the universal gravitational constant used in Newton's equation. I have made previous videos, and this is two of them. Do you know where the sun is, and do you obey the law? I will put these in the description so that they are there for your convenience. And if you are a Christian who likes science, I hope that you will enjoy those two and this one as well. So let's look at Newton's universal law of gravitation. Wikipedia states it this way. In today's language, the law states that every point mass attracts every other point mass as a force acting along the line intersecting the 2 points. The force is proportional to the product of the two masses and inversely proportional to the square of the distance between them. Newton did this work in 1665-66 when he was a young man, primarily in his 20s. And you can take this last part, this proportionality, and make it an equation. Symbol is a proportionality symbol, saying the force of gravity is the product proportional to the product of the two masses and inversely proportional to the square of the distance. Well, this statement can be made into an equation by adding a constant of proportionality. That's a general term for this. It's done for many statements like this, assuming that the statement is precise. If it's not precise, if the mass and the distance statement isn't precise, then you need to modify this until it is, and then you add the constant of proportion. So they're assuming that the statement is precise. And G is the constant of proportionality in Newton's equation. Well, the value of G was first done in 1798 by Henry Cavendish. That was about 130 years after Newton developed the statement. So he didn't know what the value of G was. And the experimental apparatus consisted of a torsion balance. This is a torsion wire. It has its own constant of proportionality, K, and it has a pair of 2-inch, 1.61 pound lead spheres. That's the red ones. Suspended from an arm of a torsion balance, and this is the arm, and this is at the center of gravity of these two, so this is balanced. It needs to be balanced in order to negate the vertical force of gravity. Here they're going to measure the horizontal force of gravity. And there's two much larger stationary balls. They're 350 pounds. Note here that most of the time I usually talk in metric, but here it's in pounds, and that's because Sir Henry Cavendish was an Englishman. So what he did was he knew if the ball went a certain angle, a certain distance, he knew what the Newtonian force was on that ball due to the torsion wire. And he made the assumption that the torsional force was equal to the gravitational force. So you have to stabilize this in an original position, balanced and not moving, and then position it between these two balls, let it go, and measure the angle. Then you have it. And you can solve for G using the Newton's equation, except he equates the torsional force and the gravitational force, and when you twist this around, you get G is equal to the torsional force times r squared over the product of the masses, and you get the value. But Newton's equation doesn't always work. His equation works most of the time, but there are exceptions, and here's three of them. The perihelion advance of Mercury, they tried to explain it using Newton's equation, but they couldn't do it. It was off, and it took Einstein and relativity to get the final answer, and I'll go into that here in a moment. There's another thing that happened in 1972 and 1982. Pioneer 10 and Pioneer 11 spacecrafts were launched. After 20 years of tracking it, they expected it to be out at a certain distance, and it wasn't there. It hadn't gone far enough, so they call this the slowdown. Pioneer spacecraft slowdown has no answer. Neither Newton nor relativity or Einstein's equation answers that problem. The speed of the stars at the edge of the galaxy. Well, that's to explain that, they invent dark matter, and that's a whole other subject. So what's the problem? Is Newton's statement precise? Is G a constant? Which is it? Or do we even know the answer? Well, let's talk about the perihelion advance of Mercury. Normally, G is measured with two masses, but as you see, and in fact, there's more to it than that, you have the Sun, you have the orbit of Mercury, orbit of Venus and Earth, and then you have Mars and Jupiter and all the rest of them. So when you use Newton's equation to calculate what this path is going to be, the two-body equation, mass 1 and mass 2, yeah, you can do Mercury and Sun, but then you got to do Mercury and Venus, and then Mercury and Earth, and Mercury, and it gets pretty complex if you're going to do it correctly. And that needs to be done. How it was done, I'm not sure, but they tracked the perihelion of Mercury for 100 years. 1859, a gentleman found out it wasn't advancing far enough. Now, the perihelion is the closest point that Mercury is to the sun, or for that matter, for the Earth is to the sun. Perihelion is a Greek word. Helion comes from helios, meaning sun, para meaning nearest. So that's the point nearest the sun. Aphelion is the usually the opposite end when it's furthest from the sun. They were tracking the perihelion point, the point that was closest to the sun, and it went too far, and they couldn't get the proper answer. Well, basically, when you measure G, you've got just two objects. I know this is actually four, but they're doing the same thing on both ends. It's all balanced. It's all perfect. This is a perfectly round sphere, and this is a perfectly round homogeneous sphere. And Newton considered in that case, you could consider the masses as a point mass in the center here and in the center there. So with the perihelion of Mercury, you're assuming that the mass of the sun is in the center and the mass of Mercury is in the center. You've got to do that for all of them. And it turns out that gravity has to know where that is if it's going to operate like that equation, or if that equation, the other way around, is going to describe precisely what gravity is doing. And when you get to an object, a situation like the perihelion advance, you don't have perfect ideal cases here. Okay, so mass distribution becomes a point to me. Then a question I ask here, how does gravity find the center of mass of a hammer? Well, it turns out that I have a hammer here, and I can try to find the center of mass of the hammer. If I grab it here, clearly that's not right. If I grab it here, that's not right, but I can find it. If I keep moving, there, yeah, I can find it, and there I got it, approximately. Gravity has to find that point if it's going to act like the equation says. And it's kind of interesting. You can drop this hammer. I'm going to drop it into my hand. And if you saw that at all, it's fast, I realize that, but you can do this at home. You can drop it, and you can see that it drops very nicely this way, where the hammer, the gravity somehow, according to Newton, magically finds this. But gravity doesn't have the time to sit there and analyze the hammer head and the handle, how long it is, what the mass is here, what the mass is there. It's got to act instantly and know that this is the center of gravity and apply the force. Well, in fact, it applies force here, 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 and here, all the way along. And even there, you got to know where this center is. You can't do that. As a matter of fact, when you look on the internet to ask the question, how does gravity find the center of mass? They don't know. There's no answer. Interesting. Well, science has repeated this experiment, this measurement, over and over again, getting better and better results. So they have better instruments and techniques in hopes of getting more precise value for G. Science relies on the fact that gravity is going to be the same day after day, year after year. Our world seems to be stable, but the universe is constantly changing. We know that the Andromeda galaxy, which is quite a few light years away, is on a collision course with the Milky Way galaxy. There's a huge change, two galaxies moving towards each other, and that's changing. That's the way God created the universe, our solar system, the planet Earth. It's very dynamic and changing all the time. Right here on the Earth, things are changing all the time. And they show this by this graph. This is the measurement of G. Measurement of G, and the average value, they're saying, is here. But from 1985 to 2015, these are the recorded measurements. I believe the red is an official recorded measurements, and sometimes it falls on this line, sometimes not. And apparently there are as individual measurements that are made, but look at the variation. It goes from 6.722 to 6.775, 6.675. The third digit goes from 2 to 5. It's not very constant, although you could argue that that's not very much of a variation. This scale is expanded quite a bit in order to show this variation. They've tried to explain it. If you look this link up and read about it, they try to say that, well, maybe it's caused by some underground movement. That's what I said. The universe is dynamic. It's changing all the time. But what I find interesting is you read in Wikipedia, the official value, or actually in this link, is 6.673889 times 10 to the minus 11th newtons meters per kilogram squared, all the way out to 6 digits. I don't know how they could go out that far and claim it's that accurate of a value when its value is moving all over the place. Well, obviously, nature is not always constant. Science needs stability and repeatability to validate theorems, postulates, and equations. When nature deviates from the normal, scientists call it an anomaly. There are anomalies, and sometime I'm going to talk about anomalies, but they're generally ignored. Yeah, they look after it, trying to explain it, but as long as they call it anomaly, that means they don't have an explanation. And some of them involve gravity. Okay, or they'll say if God intervenes in nature, and the Bible has shown us many times when he can, and there are experiences that people have even today that God intervenes in nature, healing in particular. And when this happens, the non-Christian scientists, they don't like it. They don't think it's true. And obviously, being non-Christian, they're not going to accept it as being true. As a Christian who likes science, I get it that we need to have the stability within a certain range. We can use equations, develop constants, but I call them virtual constants because they may change. They may change. 100 years from now, the value of G may be that they measure may be totally not totally different, but significantly different. And I also believe that God can intervene in nature, make things happen that science can't explain because it's not repeatable. But there is a biblical constant. Each verse of Psalm 136 ends with the statement, his steadfast love endures forever. That's King James, one of my wife's favorite verses. And it tells us that God and God's love is the true universal constant. Thank you. My name is Bob D. Hilster, and I am a Christian who happens to like science.